All right, we are back. We are going to wrap up, I hope wrap up. We might have a related rates problem at the end of class, as everybody was screaming at me before the camera started today that I chose the easiest one to do. So we may do one at the end of class, but today the goal is to cover 4.2, relative max, relative min values on a picture, on a curve, absolute max and absolute min values of a function. But we were yesterday wrapping up a problem, a related rates problem. Let's pick back up on that today and get that to a point where we have a solution. Switch to 4.2, and then kind of have time for some questions, I hope, at the end of class. All right, here's the problem we were doing yesterday as class ended. We ran out of time. Two sides of a triangle have length 12 meters and 15 meters. We already took care of units, so I'll kind of ignore that part now. The angle between them is increasing, so this angle theta is opening up at a rate of 2 degrees per minute. We changed degrees per minute to radians per minute. Actually, radians is an understood unit that's not actually written down or mentioned, so this looks like pi over 90 per minute. That's the reason why we want to use radians in calculus. It's kind of a unitless description. How fast is the length of the third side, which we've called x, increasing when the angle between the sides of fixed length is 60 degrees. So we're going to lock in a particular moment. At this instant, we want theta to be 60. Obviously, it's not always 60. It's changing. So we labeled the diagram 12 and 15. Between those two sides that are fixed is the angle theta. Opposite angle theta is side x, which is increasing as theta gets larger. So we're going to have an equation that has all these circled quantities in it. 12 and 15, they're fixed, but they're in the equation. Theta and x are also in the equation. If that's true, we're going to need to know d theta over dt, which we do. We were given that. We just converted it to a more friendly unit. dx over dt is unknown, but we want to keep it in the problem because that's the question. How fast is the length of the third side increasing? So we want to know that. So we came up with an equation that looks like this using the law of cosines. The law of cosines, let me just, in general, I could tell yesterday that that wasn't something on the tip of your tongue. So let's call this angle A, angle B, and angle C. Any triangle, it's not necessarily a right triangle. In fact, if it is a right triangle, law of cosines actually becomes Pythagorean theorem because the cosine of the included angle is the cosine of 90, which is 0, which causes that term to disappear. So if that's angle A, this would be side A. If that's angle B, this would be side B. And if that's angle C, this would be side C. So you can start wherever you want to. And there are three different versions of the law of cosines on this triangle. So let's say we want to start with side C. So side C squared is, somebody take over.
A squared plus B squared minus 2.
Doesn't that that's kind of Pythagorean theorem looking, right?
Minus
2ab cosine
of large
theta.
Okay. So the sides that we were working with A and B so that we can find C, supposedly. So A squared plus B squared minus twice their product, meaning A and B, times the cosine of their included angle. So the angle between sides A and B is angle C. So this is always the included angle. So we don't have to start with C. We could start with A. So the same pattern would make this look like what then?
C squared plus B squared.
2 BC cosine of angle A. So angle A is the included angle between sides B and C. So we could come up with the third version too, but that's kind of how law of cosines work. And the included angle happens to be 90, whether it's angle C or angle A. The cosine of 90 is 0, which drops this whole thing out, which then leaves us with this, which is our old friend, the Pythagorean theorem. All right, so there's a quick, very quick look at law of cosines, but we have it on our triangle. X is the side opposite angle theta, so we start with x squared, the sum of the squares of the other two, minus twice their product, times the cosine of the angle that they include. So the angle between 12 and 15 was theta. Does that help that a little bit? Kind of where that came from? We took the derivative as we were ending class yesterday. Derivative of x squared with respect to t. Derivative of that with respect to t is a constant, so it's 0. That's a constant. Its derivative is 0. This is a coefficient, so it comes along for the ride. Derivative of cosine theta, negative sine theta, d theta over dt. That's where we stopped, right? So what do we know, and what are we trying to find?
We need to figure out.
Okay, we want to find dx over dt, right? So that's going to be variable. Do we know everything else? I don't think we do. I think we need to do that as well in this problem. So at the particular instant that we're trying to analyze, theta is pi over 3, right? So we need to know what is x at this particular instant. We do know what theta is. We do know what d theta over dt is. This is what we're trying to find, so we want to leave that alone. It is variable. So it looks like we need to figure out what is x at this instant. So let's go back to this equation. X squared, 12 squared, that's known. 15 squared, 2, 12, 15. All that's known on the right side. And at this particular instant, we also know that theta is pi over 3. So everything on this side is known. It's a number. So we have to kind of do the button pressing on the calculator and see what we get for x squared. 12 squared, 15 squared, what is that? 144. 15 is what? 225. That'd be 30 times 12, what, 360? 360?
No.
Oh, wait, no.
360, yes. 360.
Because 2 times 15 is 30. 30 times 12 is 360. And this is where a common place where mistakes are made on the law of cosines. If this angle, when you take the cosine of it, happens to be negative, you're going to be subtracting a negative. But in this case, cosine of pi over 3 is not negative, so we don't have to worry about that. But sometimes that's a place where errors are made on the law of cosines. Cosine of pi over 3 is 1/2. So it's all arithmetic, and it kind of was arithmetic on the right side. What do we have here?
369 or 180.
69 minus 180. 189. Is that a perfect square?
No. 13.7477.
7477. That's always a question, and it's always a question that I have too. You probably have that question. How many decimal places do I keep? It might be just best to say that x is the square root of 189 when you plug it in, and that keeps however many your calculator is allowing. All right, so that goes up here. So we know what x is. Everything else we either know or we want to know. So let's start plugging in values. So here's our equation. 2x dx over dt. So x, I'm going to go ahead and put down square root of 189 dx over dt. Negative sine of theta. What is theta at this instant? Pi over 3, right?
Yes.
And then d theta over dt was pi over 90, right?
Yep.
So it looks like we need to divide both sides by 2. Divide both sides by the square root of 189. Those are gone. So punch the right buttons in the right order. Yeah, we can knock the 2's out. And that should be the rate at which the third side is changing. Dx over dt. And the units should be, what were our units? Meters and minutes, right? Meters per minute. Does anybody run that through? Everybody confident that you could, if you get to this point in the problem, you can punch the buttons and get the solution?
Yeah, if I can get there.
If you can get there, that's the issue. This is really never the issue. Occasionally it's the issue, but most of the time it's getting to that point. Okay, I'm going to leave it there. I mean, I'm confident that if you can get to that point, you can solve the problem. Anybody have it before we leave it? What if you got a negative answer?
Seems small.
Something happened, right? Some kind of sign error happened. So we should get a positive. There's a negative, and this is a negative, so their product is positive. So if we take care of signs, we should get a positive, which is what should be happening. Did I stall long enough to get an answer?
I got 0.3958.
0.3958. Meters per minute is how fast x is increasing at that particular instant. All right, let's go into max and min values on a graph. This is 4.2 in this edition of the text. We've got different kinds of max and min values. We're going to have a relative, sometimes called local, max or min. It may or may not be absolutely the highest point on the graph, but in that general vicinity, in that locality, it's the highest point in that region. We also have absolute, or sometimes referred to as global, max and min values. They are absolutely the highest point on the graph, if there is one. So a lot of graphs don't have a highest point, or absolutely the lowest point. Now, when I say point, I'm probably not writing enough here. When we talk about max and min, whether they're relative or absolute, we're talking about maximum and minimum. This is the part that usually gets left out, but it kind of clarifies what kind of answer you give. Values of the function. What are values of the function? Those are y values. So we're talking about the maximum or the minimum y values. What is the largest y value you'll ever get on the function? What is the smallest y value that you'll ever get on the function? So if it has a blank in WebAssign and says, what is the max, you're going to plug in the y value. Now, you're probably going to find the x value where that happens, but you don't want the x value, you want the y value. You want to know the highest and lowest values on the picture. Those would be y values. Highest y value, lowest y value. Let's take some actual statements from the book and highlight some things. You don't need to write these down. These are in your book. but I want to point out some things. Actually, before we leave this, let's do this. So we could have a graph that's really well behaved, and it can do stuff like this. You can also have one that comes up to a peak like this, and then turns and does kind of the typical polynomial thing. Now, if this is what the picture looks like, does this picture have an absolute max? It does not. These are all candidates. Here's a relative max, right? Derivative is 0. Here's a relative max. What's the derivative there? Undefined. Okay? But even though these are candidates for the absolute max, these values, these y values, are larger, and they keep getting larger. So we don't have an absolute max. Do we have an absolute min? Don't have an absolute min either. This is a candidate for absolute min. It's a relative min because the derivative is 0. This is a candidate for absolute min. It's a relative min. Derivative is 0. But we have values that go lower than that over here. So no absolute, and this is common for it to have no absolute max and also no absolute min. We have lots of relative max and mins. Relative max, relative max, relative min, and relative min. Notice this is not on a closed interval. This is graphed from negative infinity all the way to positive infinity. So we're graphing the entire thing. So that's very common for it not to have a lowest nor a highest y value. If we chop this on both ends and have a specific starting point and a specific ending point, then we will have an absolute lowest point and an absolute highest point. So let's move on to that in word form. Here's some definitions from your book. Don't copy them down, but let me highlight some things. Absolute max is the terminology that I'll use, but in case you see global max or that's on a question, it's asking for the same thing. So it happens at C, that's the x value, but we really want to talk about the f of C, the y value. The y value is larger than all the other y values in the domain. So the number f of C, so again, emphasis on the y value, is called the maximum value of the function. Value of the function, meaning y value. Same deal with absolute minimum. The y value is smaller than all other y values for all x's that exist in the domain. And then this is a term that kind of collectively refers to both of these. These are called the extreme values, the highest and the lowest values. So that's absolute. Now there's one thing in particular that I want to point out in the next definition, and that is local or relative max or local or relative min. So it has a local max or a relative max at C. Again, we're looking at the y values. If the y value at C is greater than, notice equal to, I think that comes into play on that question that you were asking before because all those points are in the same horizontal line. So it's okay that they're equal. F of C greater than or equal to. Now, here's where they specify, and this is the reason I wanted to look at this in class, when x is near C. So it's in the same locality. That's why it's called local max and local min. This means that the y value under consideration is greater than or equal to all other y values for all x in, and here's why I wanted us to look at this, some open interval containing C. So to be a relative max or a relative min, you have to be able to go a little bit left of there and a little bit right of there and then analyze what's happening at that point. So on my diagram over here, the reason that this is a relative max is you actually looking at the picture a little bit left of there and a little bit right of there, so some open interval containing C. And if that happens to be the largest, or at least equal to all those values, it's a relative max. This is a relative min because I'm going a little bit left of there and a little bit right of there, and of all those points under consideration in that open interval, it's as large as, if they're all the same, or, I'm sorry, as small as, or in this case, smaller than all the other y values in that open interval. Now, when we get to something that has an endpoint later, remember this terminology where they talk about some open interval containing C. You can't have an open interval if you've got an end. You can't go to the right of there. So endpoints will not be relative max and relative mins because you can't do an open interval containing the endpoint. It's an end, so you can't go one way or the other. So those won't be relative max and relative min endpoints. They will certainly be candidates for absolute max or absolute min because they may in fact be the highest point or the lowest point that's plotted on the graph, but they will not be relative because you can't fulfill all the conditions in the test that you need to. You can't find an open interval containing C because C is an endpoint. All right, this term is mentioned again, this extreme value. If the function is continuous, that's probably worth underlining. So throw out those that are not continuous because something else strange happens there. On a closed interval from A to B, then that function has an absolute max and an absolute min if we go on a closed interval. So let's see what a picture looks like of that. Actually, I've got one. Let's use this one. Let's look at this picture on a closed interval. Let's say from, since this is where the picture goes, from -2 to 2. Now, we'll come back and validate some of these points, why this is a relative min and an absolute min, right? This is a relative max, but not an absolute max. If you have a specific starting point, and the graph does its little deal here, and we have a specific end point, then you have to have an absolute max and an absolute min, if it's continuous. Agreed? So you start to draw it, and you keep drawing it without any breaks to a point where you stop drawing it. It's got to have a lowest and a highest value. So what are the candidates? I think we're about to start this. What are the candidates for absolute max and absolute min? Well, the endpoints, right. So one of the things, or in this case, one of the entries, we have to check the endpoint. So in this problem, we would need to know the f of -2. That's a possible highest or lowest point on this graph. And the f of +2 is also a possible highest and lowest. And in fact, in both cases, there's a tie. So they're both the highest points on the graph. And when x is 2, I think it's 18, but let's check it out. It shouldn't matter, right? If we put in -2 or 2 because we're raising it to the fourth, and then we're squaring it, right? So this is an even function. Remember that from early in the course? So 2 to the fourth, there's 32, 18, is that correct? Am I remembering the right number? I think the arithmetic yields 18. The graph might not look like that, but let's assume that. I think this actually probably stops a little shy of -2 and of 2, but let's assume that this is the point 2, -2, 18. So check the endpoints out. They're possible highest and lowest values. Where else could we get a highest and or lowest value on the entire picture?
Negative 1, 1.
Okay, what's happening there?
Could have value 1, they could be mean.
Isn't the slope of the tangent line
0.
0, right? So we want to find where the derivative is 0. That's a candidate for absolute maximum. Here's another place where the derivative is 0, which we'll validate this in a little bit. And here's another place where the derivative is 0, right? So are any of those places on this picture where the derivative is 0, are any of those absolute max or min values? Yeah. Negative 1. If you put negative 1 into the function, or if you put 1 into the function, we should get the same thing, which is what? 0? Now, can you, when you look at that function, and be honest with this answer, when you look at that function and you say, oh, yeah, the lowest value you'll ever get on that function is 0, can you tell that? I can't either. So very rarely will you be able to look at a function. Occasionally you can. I mean, you can look at a function like this, and you can tell what the smallest value you're ever going to get out of that function is, right? Because this at its smallest is 0, and then you're going to add 5 to it. So that's the lowest point on that graph. Sometimes you can tell that. But I can't tell that, and I doubt if you can tell that by looking at this. So we need to take places where the first derivative is 0, as well as the endpoints, and we're forgetting something here,
Where the derivative doesn't exist.
where the derivative is undefined or fails to exist. Those are also possible highest and lowest points. Now, do we have any of those kind here? No. The derivative of this is a polynomial, so the derivative is also a polynomial, so it will never fail to exist. But we do need to check out all of these three things. Endpoints, where's the derivative 0, and where's the derivative undefined? Somebody had a question or comment? No? What do we call those? Where the derivative is 0 and where the derivative is undefined? Critical points. So we'll come back to this picture and basically validate that these are in fact the places where the derivative is 0. So there's the, before we leave this, there's the absolute max, right? 18 on this closed interval. And the absolute min is 0. Absolute min is 0. And it happens twice. There's a tie, but they're both the lowest points on the graph. So again, we want to give y values when that happens. All right, again, you don't need to copy these down. These are in the book, but let me point out some things. If the function has a local max or min at C, and if the first derivative does exist, then the first derivative is 0. Well, that takes one of the two possible critical values out because the derivative doesn't exist. I think of more value is this definition. What constitutes a critical number, or a lot of times we call it a critical point, is a number C in the domain, and the derivative is either 0 or the derivative does not exist. So those two things that we just wrote down on the other picture, if we can find those, then we've got the candidates that we want. Add to that the endpoints, if in fact it does have endpoints, and we've got all the candidates for local and absolute max and min. So if a function has a local max or min at C, then C is a critical number. Notice, what did it leave out here? Endpoints, right? Why did it leave out endpoints? Why are they not local max or mins?
Because you can't look to the left or the
Because you can't create an open interval on either side of that endpoint, so therefore they can't be local. So these specifically is left out. Even if it is a place where the derivative is 0, even if your graph looks like this, so you've got an endpoint here, it does this, and then it comes up and is turning, and that is a place where the derivative is 0. That is not a relative max. Right? Even if the derivative is 0 there. Why is it not a relative max? Because we can't create an open interval that contains this point, so it's not even a candidate. Now, it might be absolute max. In fact, it is, right? But it's not a relative. Not a relative max, but it is an absolute max.
What if it like goes flat? Like, could that still be?
Okay, and that's kind of related to that WebAssign question, right?
Right.
Where it's flat for a while. So you've got, let me see if I can kind of resurrect that picture. Doesn't it do something like this?
Mm-hmm.
And then what's it do? Go back up?
Yeah.
Okay. Now this point right here, if I'm going to decide if that's a relative max or min, right? I need to be able to go a little bit left of there and a little bit right of there. That's probably too far, but so that the diagram won't be too cluttered. Is this y value of this open interval, and all these y values that I've used, is this greater than or equal to all those values? Is this y value less than or equal to all those values?
less than or
It's less than or equal to, right? So this point would be
Relative.
a relative min, right? And I don't know what the rest of the picture looks like, but if this is as far down as it goes, it could also be an absolute min. But I think this picture over here gets lower than that, right? From WebAssign. Okay, yes, Ken.
On the first graph, you see what's got the endpoint? It has a relative max and an absolute min, crap like that. Well, would the endpoint be a relative min because there's an absolute max on that graph, or absolute min on the graph?
This one?
Yes.
This cannot be a relative min.
Not even if there is a maximum min already on the graph.
Right.
Okay.
So an endpoint will never be a relative anything,
Gotcha.
okay? But it could be an absolute one or the other, max or min. And the reason is because we can't create that open interval. We can't go left of here to determine if, in fact, it's a relative min. We can't go right of here. So by definition, according to these authors, endpoints will never be relative max or relative mins. Question?
Okay,
Mandy.
if there's a point right where it's horizontal, like just right in the middle,
Yes.
what would that be?
Okay. So that was the next place I was going to go.
Okay.
Thank you for leading me there. I need some help from time to time. Now, if we're going to decide if this is a relative max or min, we need to be able to go a little bit left of here and a little bit right of here. So we're only concerned with this part of the graph, right there. Is that point, that y value actually, the f of c in this case, in this region right here, is it the highest y value of all these points under consideration? It is, right? It's the highest. There aren't any higher than it. They're all tied, so they're all as high as one another. Okay? Is it also the lowest y value in that region? Yeah. They're all the same, so not only are they all the highest, they're all the lowest. So is this a relative max? It is. Is this also a relative min? It is. Now we don't have endpoints here, but for the whole picture, we know it's not an absolute max because these are higher. And for the whole picture, I can't remember what this does, but I know it comes down here and ends. So these are not absolute minimum values either. But that point right here is a relative max and also a relative min, which seems a little bit odd because, they're all in the same line. But by definition, it's both of those. Now, what has not been mentioned here, suppose we have a function that has endpoints. So let's say it starts here and it ends here. So it's got a closed interval. So here's A, and here's B. So a fixed starting point and a fixed ending point. Another word that was used in there was that it needed to be continuous, right? If, for example, it's not continuous, and that could be discontinuous a lot of ways. Let's say it has a vertical asymptote right here. And this goes up. And this goes down. Actually, that's increasing, right, from left to right. Do you see what happens when it's not continuous? Is it guaranteed to have an absolute max? This one doesn't have an absolute max, right? Is it guaranteed to have an absolute min? No, it's not. This one doesn't have an absolute min. So when you take that descriptor, that continuous descriptor out of there, if it's not continuous, then you can't make that same conclusion. If it is continuous, then it will have an absolute max, and it will have an absolute min. And there's a lot of ways it could be discontinuous. This is just one way to illustrate that it doesn't have to have absolute max or min. All right, the picture that we had, that fourth degree polynomial, looked like this. So if we were looking for critical points, what do? Okay, one of the ways is take the derivative, set it equal to 0. What is the derivative of this function? Excuse me. 8x cubed minus 8x. Is that right? And we want to set that equal to 0. Probably we would want to factor it. Each term has an 8x in there. If we factor that out of the first term, what do we have?
X squared minus 1.
Okay. Everybody agree with the factors, or with that part, factoring out 8x? And then we kind of luck out and we're able to factor again. X squared minus 1 is?
X was 1.
Good. Now, we're setting that equal to 0, so we can set each factor equal to 0. I guess technically 8 is a factor, but you could set 8 equal to 0, but don't expect to get too many solutions from that one. So let's set 8x equal to 0. That is 0 when x itself is 0, right? X plus 1 equals 0 when x is negative 1, and x minus 1 equals 0 when x is 1. Does that seem familiar to what we had pictured on that graph? Weren't those the three places where we had relative max and min values?
Yeah.
Now, we don't know the points yet. I wrote down critical points. We have the x values where those occur. Where do you get the y values? You plug it back into the original. Anytime and we're going to be dealing with first derivative and second derivative in this chapter. So whenever you're finding these things, critical points, and you find the x values, make sure you go back to the original function. So we want the f of 0, the f of negative 1, and the f of 1. Plotting points, go back to the original. We're going to be dealing with points of inflection soon in Chapter 4. So we want to, when we find what we think is a potential point of inflection, we found the x value. To find the y value, you go back to the original function. So the f of 0 is what? 2? the f of -1 should be the same as the f of 1 because it's an even function. 0? No. So there's 0, 2, -1, 0, and 1, 0. Now, if the derivative is 0, that means the slope of the tangent line is 0, which means it's what kind of a tangent line? Horizontal, right? So there are horizontal tangent lines there for this particular kind of critical point. Back to our picture. Any question about anything that's there? Here's our picture. Isn't that what we found at this point, that the derivative was 0, the slope of the tangent line was 0? Here's another critical point, the slope of the tangent. So if you want to think of that as kind of a place where the curve is instantaneously flat, that's exactly what happens. When you have a derivative equal to 0, we had one here, at that instant, the curve is basically flat. As it approaches there, it gets flatter, and as it leaves there fairly flat. But where the derivative is 0, so you can actually find those points. Let's say one of those points is here. I usually just draw a little line segment, and I've got another point that's here, because I want to remind myself that the curve, as it comes into there and as it leaves there, is fairly flat. So the curve either does this or this, right? As it comes into that point, it's got to do one of those two things. How does it leave here? Well, it leaves here fairly flat and either goes back up or goes back down. And it could be some combination of those. So it might increase into here, get flat, leave here fairly flat, and continue to increase. But as it approaches, it gets flatter. At that instant, it is flat. And as it leaves fairly flat. So that's probably not a real strong mathematical term, but it helps me picture these things when I know it's flat at that point. Same thing here. It enters here fairly flat. Whether it's decreasing into there or increasing into there. So you can see all the possibilities of combinations. You could have, at a flat place, you could have it decrease and then increase, and now you're dealing with a what? Relative min, at least a relative min. It could increase into here and decrease out of here. Now you're dealing with a relative max. So you can see how those things that we've been talking about are actually created. Now, our function was this. And we did this. And we found 3 places where the derivative was 0. Do we need to search for any places where the first derivative is undefined? Give me some good reason why we don't need to do that.
Oh, no.
Besides that we're running out of time. That's not a valid reason.
It's a polynomial.
This is a what? Polynomial, right? Polynomials don't have those kind of places. They don't do this kind of stuff on their picture. They're nice, smooth transitions, right? Continuous. Smooth, meaning no abrupt changes in direction. No discontinuities, no abrupt changes in direction. If you took the derivative of a polynomial, you get a polynomial. It's never going to be undefined. So we won't use that at all on polynomials. We're not going to have those kind of critical points. All right. Too many pages today. Sorry. Let's start this example. We've got about 3 or 4 minutes. Let's see how far we can get with this. Got to have our daily dose of trig. Actually, that's not addressed yet. That's very soon to follow. His comment was about taking the second derivative, setting it equal to 0. We're soon to do that, but right now it's critical points. Critical points are where the first derivative is 0 or where the first derivative is undefined. So let's find absolute and relative max and min values on this closed interval. Does it have to have an absolute max and min? We've got a closed interval. Is this continuous?
Yeah.
It is continuous. So we will have an absolute max and an absolute min, and we possibly might have some other places where they are relative max and min. At some point in time, we're going to need to find the endpoints. Why don't we go ahead and get those out of the way? So we need the f of 0. What do we get for the f of 0? 0? And what is the f of 2 pi? Well, that's 2 pi, and this is 0, right? So 2 pi minus 0, which is 2 pi. So there's our endpoints. 0, we put it in, and it kicked out 0. 2 pi, we put that in, and it kicked out 2 pi. So that is a possible absolute min, and that is a possible absolute max at this point in time. Okay, let's start this process, and we'll probably have to finish it tomorrow. Derivative is what?
1 plus 2 cosine.
1
Okay,
minus
2 comes along for the ride, right? Actually, a minus 2.
Yeah.
What's the derivative of sine of x?
cosine x.
Cosine of x. And what do we want to do with the first derivative?
Set it equal to
Set it
0.
equal to 0. We want to find those flat places. So 1 minus 2 cosine of x equals 0. 1 equals 2 cosine x. Cosine x equals what? 1/2?
Yep.
Now, are we searching for all values where this occurs?
Just between
No, we're just searching from 0 to 2 pi. So where in that interval is the cosine of some angle equal to 1/2? Pi over 3?
You added 2 cosine x plus.
Where else? So that'd be the equivalent of 60, right? There's a lot of thought processes going on here. Where's the cosine positive, right? Is one of them. Cosine's positive in the first quadrant. We got that. Where else is the cosine positive? In the fourth quadrant,
Yeah.
right? What's the fourth quadrant angle whose cosine value is 1/2?
5 pi over 6.
Okay?
No,
5 pi over 6.
Yeah.
Is that right?
No.
No.
What do we want the reference angle to be?
5 pi over 3.
We want a reference angle of what? Pi over 3? Down here?
Yeah.
So what would that be all the way around to there where that reference angle is pi over 3?
5 pi over 3.
5 pi over 3?
5 pi over 3, not 5 pi over 6. Are we?
Does that work?
Yeah.
Okay, we're out of time. We'll finish this tomorrow. If you have questions from WebAssign, come by my office this afternoon. Or email me.